Essentials of the Earth's climate system. So we are still on chapter 5. Last video we covered the chapter 5 general circulation. We talk about some factors and meridional cells and zonal winds. And we're going to talk about that starting with the development of the conceptual models of the general circulation. So the earliest attempt to suggest mechanisms for the general circulation of the atmosphere was introduced by Edmund Halley in 1685. He indicated a thermally direct meridional cell with maximum heating in low latitudes. Air rises and flows forward and sinks as it cools to return equatorward. In 1735, George Hadley improved on this by noting the effects of the Earth's rotation in deflecting the flows to the right in North Hemisphere. However, the scheme overlooked the westerly wind belts. A more complete picture was provided in 1856 by William Ferrel, who proposed a three-cell model similar to that of Rossby in 1941, with two direct cells bounding an indirect one in middle latitudes. Ferrel advocated the role of angular momentum conservation to account for the westerlies. The problem of strong upper westerlies in middle latitudes was only recognized in the 1940s. It is important to note that the indirect mid-latitude cell implied upper easterlies rather than westerlies. The solution came in the 1950s with the recognition of the role of horizontal eddies, short waves in transferring energy and angular momentum forward. Nowadays, the view is of a Hadley cell in low latitudes and horizontal eddies in mid-latitude. In same location and seasons, there may be a small direct cell in high latitude. Okay, let's move on to the zonal wind belts. The pattern of global winds at the surface is arranged in the three-zone west to east belts in each hemisphere. There are the easterly trade winds in the tropics, separated from the mid-latitude westerlies by the subtropical high-pressure belt. The westerlies blow around the equatorward side of the subpolar low-pressure systems, which have on their polar margins a small belt of polar easterly winds. These easterlies are best developed around Antarctica. In the Arctic, there is no permanent high pressure, although there is an anticyclone over the Canadian Arctic in spring. In the middle and upper troposphere, the wind pattern is much simpler. Over both poles, there is a deep polar vortex with extensive westerlies blow around the subtropical high-pressure centers extend upward into the troposphere, and in the tropics there is a band of weak easterlies extending from the surface into the troposphere. Here it shows the 500 millibars contours for January and July in each hemisphere. In the southern hemisphere, the westerlies are mainly zonal, but in the northern hemisphere, in winter, there are three major planetary waves or long waves. Around the hemisphere, this is termed a wave number three pattern, where where the waves have an average spacing of 120 longitude. The wave troughs are located over East Asia, East North America, and Eastern Europe. In summer, there is a single well-developed a wave over Eastern North America. The waves the waves in winter are attributed to the combined effect of topography, the Tibetan Plateau, the Rocky Mountains, and strong land-sea temperature differences on the atmosphere. Land temperature differences on the atmosphere in the northern hemisphere. These centers over the Iceland and the Aleutian Islands that tilt westwards with height into the cold air. Before we can consider the effects of mountain barriers on flow, we must introduce the concept of velocity. So this is the rotation of an air parcel. It can arise from motion in a curved path around a low or high pressure center, giving rise respectively to synchronic or antisynchronic relative velocity. Relative velocity can also result from differences in wind speed, horizontal shear across an air current. The two effects may strengthen one another or cancel out. Synchronic antisynchronic velocity results when in the northern hemisphere the air is moving faster on the left right side of the current veered downwind. The patterns are opposite in the southern hemisphere. Synchronic relative vertical velocity, that about a local vertical axis, is defined to be positive. Antisynchronic relative velocity is negative. In the northern hemisphere, positive relative velocity is in the same sense as the Earth rotation. So these long wave or planetary wave in the middle troposphere were first described by C.G. Rossby in 1939 and hence are often referred to as Rossby waves. Typically, there are between 2 and 4 such long waves in the northern hemisphere westerlies. They tend to move slowly westward, whereas shorter waves number from 6 to 12 around the hemisphere move eastwards, are associated with cyclones at the surface. The land effect involves the development of a low-level baroclinic frontal ozone zone due to the temperature contrast between cold land and warm ocean, and this is associated with an upper trough in the cold air to the west. In winter, the orographic and thermal effects combine. In summer, there is only a single planetary wave over eastern North America, mostly due to baroclinic effects. The westerlies of the northern hemisphere are much weaker in summer than in winter, but the southern hemisphere there is almost no seasonal change due to the presence of Antarctica. The westerly wind belts have within them are the subtropical and polar front jet streams, as described here. Consequently, in the westerly wind belt, wind speed normally increase with altitude up to the top of the troposphere. The hemispheric westerly circulation alternatives at irregular intervals of about 3 to 6 weeks, but between a state where the hemispheric flow is strongly zonal and one where it breaks down into a cellular or blocking pattern. This blocking by a persistent high-pressure system disrupts the normal west-east movement of mid-latitude cyclones and causes anomalies of weather conditions to occur over a wide region. Blocking is most common in the winter half-year and is more developed in the northern hemisphere because of the hemispheric long-wave structure that is attributable to the land-sea temperature contrasts and the topography of the northern continents. The most common locations of blocking heights are in the northeastern Atlantic over Alaska and the northeast Pacific, over the Ural Mountains, and over northeastern Canada in the southern hemisphere, where there is less land-sea temperature contrast. The primary area of blocking is over New Zealand. Blocking may set up a ridge extending polarward from one of the subtropical cyclones, or it may form a separate high-pressure center and cause a split in the jet stream and storm path, with some systems going north and others to the south around it. A cutoff may form in lower latitude in associate with the blocking high. Figure shows where many of these tend to occur. Blocking patterns may persist for a month or more, and so are important components of regional anomalies of weather and climate. So the work circulation, as you see from here, is in a west and easterly height across section through the global equatorial zone. So this zonal circulation in the tropics, there is a series of 3 major east-west or zonal vertical circulation cells. These have an upward arm over the heat source in each of the 3 equatorial continents, South American, Africa, and the maritime continent of Malaysia. The islands of Indonesia and the Philippines, each of these locations is the locus of a heat low, providing strong convection. In the upper troposphere, the air diverges, flowing east and west to descend over the subtropical anticyclones in the eastern parts of the oceans. These cells are known as Walker circulations, named after Sir Gilbert Walker, who first identified the southern oscillation. They play a major role in tropical weather regimes. Data on the sea surface temperature gradient across the equatorial Pacific Ocean indicated the Walker circulation and the Hadley cell in the Pacific. The upper and lower parts of the figure show 2 different modes of Walker circulation. Identify a strong and weak phase of the Southern Oscillation Index, SOI, Southern Oscillation Index, strengthening during the 20th century, resulting in an enhancement of both